Okay, so in this video we're going to be looking at mean and standard deviation. So previously we've considered the median to describe the centre of a distribution. So in particular when we looked at the box plots most recently, the median is a really important measure of centre, and when we're describing a box plot we're referring to shape, centre and spread, we use the median as the measure of centre. An alternative measure of centre is the mean, and similarly, up until now, the measures of spread that we've referred to have been range and or interquartile range, but in this section we'll be introducing the standard deviation as a measure of spread. You might remember a few videos ago we looked at how to use the CAS to find the 5-figure summary. And we use one variable statistics to do that in our CAS, and part of the list of statistics that we get the 5-figure summary, but we also get the mean and the standard deviation. We'll review how to find that in this video as well. So the mean is something most of us should be pretty familiar with. When we often refer to the average, we're talking about the mean. And so the mean is obtained by adding up all of the data values and then dividing by the number of pieces of data. So in words, the mean is equal to the sum of the data values, sum meaning add, divided by the number of data values. As a mathematical expression, we can write it like this. So we use this x with a bar above it to refer to the mean, and that's the notation that your CAS uses. And this symbol here refers to the sum. So it's the sum of the x values, the sum of the data values divided by n, which is the number of data values. Okay, they're all quantities. Your CAS uses that notation to refer to the mean. Your CAS also brings that up when you do the one variable statistics, and it also gives you n. So if you've entered all of the data into your CAS already, I mean obviously you can get the mean straight away, but you can also get the sum of all the data values and the number of data values. So again, we'll review that in a minute. Okay, so let's think first of all about the mean versus the median, because there are certain situations when we would choose one over the other as a better measure of centre. So here I've got 3 data sets, and for each of those data sets I want to calculate the mean and the median. What I want to be clear about is that all 3 data sets essentially have the same, well, they do have the same central values. Okay, so all I'm changing from one data set to the other. In the first data set, 13 and 28 are both reasonably close to the next value. Okay, in part B, the second data set, I've kept 13 as it is, but I've made the upper value much larger. And in part C, I've kept 28 as it is, so it's still quite close to the data set, but I've made the lower value much lower, the minimum value much lower. And we want to have a look at the impact of that on the mean and the median. So median we know is the midpoint of the data set, the middle value of the data set. All 3 of these data sets have 7 pieces of data, and so the middle is 7 plus 1 divided by 2, the 4th piece of data, that value there. So in all 3 data sets, the median is 20. So even when I change, the upper value or the lower value here, the median doesn't shift at all, okay? The mean, however, let's calculate that. So let me control divide to bring up a fraction template. I'm going to add up, my data values on the top, 13 plus 15 plus 15 plus 20 plus 24 plus 25 plus 28. And dividing by, what have we got? 7 pieces of data. Control Enter to get a decimal. Okay, so in this instance, the mean and the median are the same. Okay. In part B, I'm just going to edit my previous calculation because all I need to do is change the 28 to a 48. Control Enter. The mean now is 22.9. Correct to 1 decimal place where necessary. And part C, again, I'm just going to edit the original calculation. The 28 stays the same this time, but the 13 changes to a 1. Oh, Control Enter, sorry. So to 1 decimal place, that's 18.3. Okay, so what we find here is that the first set of data is relatively symmetric. And we know that it's relatively symmetric. We can sort of see that by looking at it. It's harder to see without a sort of graphical representation, but you can probably see that, you know, the data values above the mean and below the mean are similar. Okay, so it's roughly symmetric if we were to plot it out. But also the fact that the mean and the median are the same tells us that the distribution is roughly symmetric. We'll have a look at that a bit further on graphically. Part B, we've got this big number as a maximum value. It might even be an outlier. I'm not going to bother to calculate whether it's technically an outlier, but it's significantly larger than the rest of the data, so quite possibly an outlier. And what we see here is that the median doesn't change from the previous data set when we change the upper value to a much larger outlier value, but the mean is changed. Okay, this much larger value, when we're adding up all the data and dividing by the number of pieces of data, that's going to pull on our mean up towards this way. Okay, similarly in part C, when we change the minimum value to something quite a lot lower, it's not as much of an outlier as 48 was in part B, but it possibly is still an outlier. What we see again is it has an impact on the mean. So the median remains unchanged when we introduce an outlier to the data set, but the mean changes and it is pulled. It means it's going to pull the mean down this way because you've got a smaller value in your data set. So when you add up all of your data values, it's adding up to a smaller value, and therefore when you divide by 7, you're getting a smaller value. Okay? Whereas here, when you add up all your data values, you're getting a bigger value than when you add up those data values. You're dividing by 7 again, and so a larger number divided by 7 is going to result in a larger number than what you got in part A. So having this sense of how outliers, not even technically outliers, but potentially, you know, significant spread and some slight outliers, or certainly if there's significant outliers, the mean is sometimes not considered a good measure of centre, and we would stick with the median. So when would you choose to use the median over the mean? We would use the median, so I'm going to say the median is a more reliable measure of centre when the data set contains outliers. So a common example where we frequently see the median quoted, well, actually speaking, you know, in terms of schools frequently quote, when they quote their ATAR results at the end of the year, they usually quote their median ATAR rather than their mean ATAR, because their median ATAR isn't skewed by outliers. And for most schools, their outliers are likely to be at the lower end. Therefore, if they've got outliers at the lower end of the data set, their mean would be lower than their median, and so therefore when a school is trying to promote themselves, it is in their interest to quote the higher average value, that is the median, instead of the mean. Another example where median is commonly used is in house prices. You'll see, you know, newspaper articles talk about the, you know, median house price in Melbourne or median house price in a particular suburb has gone up or down or is higher than the median house price in another suburb. So they tend to talk about median house prices rather than average house prices. And again, that's because there can be significant variability and hence there can be outliers in the data set. You know, you might have a suburb where the vast majority of houses are sold for around, you know, I don't know, 800,000, and then there might be a couple of, you know, an area where there's a couple of sort of $1.5 to $2 million houses, and, you know, averaging is going to be skewed by those outliers, whereas talking about the median is going to give a more realistic idea of the centre of the data set. Okay, so another sort of interpretation allowing you to sort of compare these two things, we know the median gives the physical centre of the distribution. So if each data point is a rock and you line all those rocks up in a row, the middle rock is the median. Okay, so it's a physical middle. The mean gives us the balance point of the distribution. And what that means is that the sum of the distances of each value, so that sentence is hard to interpret. I'm going to try and explain it with these diagrams to help me. So what it means is, if we look at all of the data values that are above the mean, and we work out how far away they each are from the mean, and we add up those total distances from the mean, it would be the same total distance above the mean as if we did the same thing for the data values that are below the mean. So if we took all the data values that are below the mean, worked out how far away from the mean are they, and added up all of those distances, we should get the same total distance below the mean as we get above the mean. Okay, so it's sort of a tipping point. So if we imagine our data set on a scale, so it's not a very good shaped triangle here, but if we imagine, this is a seesaw kind of thing, okay? So the whole thing can tip, this way or this way, depending on, if it doesn't have even weight on either side. So the idea, though, is it's not just about having even weight on either side, it's actually about the thing being balanced. So here we have a symmetric distribution. When we calculate the mean and median, we find that they're the same thing. So in this case, the mean and the median are both 7, and this is actually a perfectly symmetric distribution. So this 10, that's 3 away from the mean, 11 is 4 away from the mean, and 13 is 6 away from the mean, and here 4 is 3 away from the mean, and 3 is 4 away from the mean, and 1 is 6 away from the mean. And if we add all those up, we've got same distance on either side, and so the distribution, that's what tells us where the mean's going to go. Okay. When we look at a positively skewed distribution, so here's the list of data here. Here I've placed it on this sort of balance number scale. Okay. We can work out that the median, we've got 6 bits of data, the median is in there, 2.5, and we can add up all the data values and divide by 6 to calculate the mean as being 3.5. So here we've got the mean is higher than the median when the data is positively skewed. Okay, and the mean, again, think about the mean as this idea of a tipping point. So we've only got 2 values above the mean and 4 values below the mean, but that's not the same as the median. The median is about us having the same number of data values either side of the median, which is why here 3 data values above, 3 data values below. That's why the median sits there. Okay, but the mean, the value of those numbers is important. Okay, so if we look at the numbers, the 2 numbers above the mean, that number is 0.5 away from the mean. And that number is, what's that going to be, 5.5 away from the mean. So the total distance is 6 above the mean, okay? If we look at below the mean, this is also 0.5, 3, and then we've got 2 data values that are 1.5 below the mean. Both those 2s are 1.5 below the mean. And then 1 is, what's our mean again? 2.5, so, mean is 3.5, so 1 is 2.5 below the mean. So if we were to add up those values, those distances below the mean, 1.5 plus 1.5 is 3, plus another 0.5 is 3.5, plus 2.5 is also 6. So that's why here's where our mean sits between those 2 values, because that's going to ensure that the distances either side of the mean are balanced. So it's sort of like imagining, if all of these little boxes weigh the same, it's not just about having the same number of boxes either side of the scale. It's also, having this box further away is going to have greater impact than these boxes that sit close to the mean. Okay, so it's about that balance or that tipping point is what the mean's about. And when we have a negatively skewed distribution, here's the data set. We can see that the median is going to be 7. The mean, if we add them all up and divide by the number of pieces of data, is 6. And so here, when we have a negatively skewed distribution, the mean is less than the median. And that's really because we've sort of essentially got outliers down here that are dragging the mean happening this way, dragging the mean up this way. Here we've got outliers up this way that are dragging the mean that way compared to the median. Again, if we think about this tipping point kind of idea, this balance point, that's 2 below the mean, and that's 5 below the mean, so we've got a total of 7 over here. And then up here we've got 1 and 1, 1 above the mean, 1 above the mean for those 2 7s, 2 above the mean for the 8, and 3 above the mean for the 9. And if we add up 3 plus 2 plus 1 plus 1, we also get 7. Okay, so that's why here's where our tipping point is. But if we're just interested in the number of pieces of data, okay, this is the median here, that one. You've got 3 pieces of data above that and 3 pieces of data below that. Okay, so this idea though of when the mean is likely to be bigger than the median, i.e. when we have a positively skewed distribution, when the mean is likely to be less than the median, i.e. when we have a negatively skewed distribution, and then when the mean and median will be the same, roughly the same, is when we have a symmetric distribution. Okay, we also want to talk about standard deviation as an alternative measure of spread. So range and interquartile range both talk about the spread about the median, whereas the standard deviation is a measure of how the data is spread out about the mean. Okay, so if we're quoting the mean as the measure of centre, we really want to be thinking about the standard deviation as the measure of spread. If we're quoting the median as the measure of centre, we really want to be thinking about the interquartile range and or the range as the measure of spread. Okay. So the difference between each data value and the mean is called the deviation. Okay, if we've got a data set with a mean of 5 and you've got a data value of 8, its deviation is 3. It's 3 away from the mean. Okay. When we're calculating the standard deviation, we essentially want to find the average deviation, the average distance of each point away from the mean. Okay. However, this presents a few computational problems when we actually go through doing that. As you'll see, because some of the deviations are going to be negative. So if we consider a really simple small data set, so I've got 5 pieces of data here, and if we calculate the mean, we add them all up, we divide by 5, we find we get a mean of 11. If we think about each of our data values, this is just the data set copied into a table, we calculate the deviations, i.e. how far away is that data value from the mean. Okay. Now it's not just how far away is that data value from the mean. What we're actually doing every time is taking the data value minus the mean. Okay. So when the data value is 3 and we take away the mean, which is 11, we get a deviation of negative 8. When the data value is 8 and we take away the mean of 11, we get a deviation of negative 3. When the data value is 12 and we take away the mean of 11, we get a deviation of positive 1. So we're going to get negative deviations when the data values are below the mean, and positive deviations when the data values are above the mean. Okay, and what we should find here is that these positive deviations, if we add them up, 8 plus 2 plus 1, that's 11. These negative deviations, if we add them up, negative 8 plus negative 3, that's negative 11. And this is about that balance point, that tipping point. Okay, so the negative deviations should always add up to the same thing as the positive deviations. That's how the mean works. So what this means is if we were to average all of these deviations, so if we added them all up, you'd end up doing a negative 11 plus 11, which would be 0. They would add up to 0, and that's by definition how the mean works. Okay, so if we just added up the deviations, we would always get 0. And so therefore the average of the deviations would always be 0. But we don't want the average of the deviations, we want the average of the distances. We want to be able to think about this as positive 8 and this is positive 3. Okay. However, that's not that easy to do mathematically, so instead of just changing the negatives to positives, because you've got to think about these processes have to apply over a very large data set potentially, what we do is we square all the deviations. So negative 8 squared is positive 64. Negative 3 squared is positive 9. 1 squared is 1, 2 squared is 4, 8 squared is 64. Okay? And when we do that, because when we square negative numbers they become positive, we now only have positive values. Okay, so that gets rid of our negative problem. And then we could average those values, so add them up and divide them by 5. However, there is a slight statistical issue with that, a slight computational issue with that, and it's to do with the fact that we're in further maths usually dealing with small samples of data rather than large populations of data. And so actually in further maths we use something called the sample standard deviation, which means that we divide by the number of pieces of data, minus 1. Okay, so here we've got 5 bits of data, so n equals 5, which means n minus 1 equals 4. So we're going to add up all those squared deviations and divide them by 4. It's an adjusted average. Okay. Again, you don't really need to understand that or why. You're not going to have to work out this process. I just want to give you a sense of what's happening with the standard deviation, what the standard deviation is actually calculating. We'll be able to use our CAS to do the calculation for us. Okay, so then this is an average of the squared deviations. Okay, so that's not the average deviation. So actually, or the average distance from the mean. So we're then going to square root this average of the squared values, so that we then get essentially an average distance away from the mean, which is what the standard deviation is. So the formula for the sample standard deviation is this. Okay, as I said, you're not going to need to execute that formula. I just wanted to do it once and talk through it so you have some understanding of what the standard deviation is. Okay, so our standard deviation is 5.96. And a rough interpretation of this would be to say that on average, each value in the data set is about 6 units away from the mean, about 5.96 units away from the mean. Okay, so that's what's happening here. So what we're seeing here is the mean is 11, okay, this value is 1 above the mean, this value is 2 above the mean, this value is 8 above the mean, this is 3 below the mean, this is 8 below the mean. On average, the average distance from the mean is about 6. Okay, so that's what our standard deviation is telling us about. Okay, let's just review how we calculate mean and standard deviation with our CAS. So if I were to, let's just take this very simple data set we had here. I'm going to need a list and spreadsheets page, so we need a document, a new document with a list and spreadsheets page, so number 4. I'm just going to call my column data. I don't even need to call it anything if I don't want to, but I encourage you to get in the habit of doing that. It means you do the same thing every time. 3, 8, 12, 13 and 19. Okay. Then I'm going to go to menu, 4 for statistics, 1 for stat calculations, short for statistical calculations, and then 1 for one variable statistics. Okay. My X list, so where is your data? See, by default it chooses column A, so if I just put my data in column A, didn't give it a name, I could just stick with what's happening there. If I press across here and access the drop down menu, it'll show me any variables that I've got defined. So my variable is called data. The bottom box here is telling me that it's going to put the results in column B. That's fine, that suits me, there's nothing else in column B, so that's okay. So press OK, and I get this one variable statistics that we've seen before when we calculated the 5-figure summary. So we've got this X bar here, that's our mean. That matches with what we calculated by hand for this particular data set. We've got the sum of all the data values, 55, which we've calculated over here. That's what we did there, and we added them all up. We've got our standard deviation, which is we want this SX. This sigma x, the next line here, the value in row 6 of the spreadsheet, that's also standard deviation, but that's a population standard deviation, and we don't use that one in Further Maths. So we're always going to use this SX, and that 5.95, that matches what we calculated here. Where's my calculation here? Square root of 35.5 was approximately 5.95, that's a rounded value. Sorry, 5.96, that's a rounded value, and that matches perfectly with what I'm seeing my CAS having calculated. Reminder, there's also there's your N value, so there's 5 bits of data, and then there's also the 5-figure summary down here. So you get all that information all in the same calculation. Okay, so the work today is from exercise 2F, calculating means and standard deviations, and having some sense of what it is that you're actually calculating. In particular, mean, how that compares to the median.